chapter 18 is about sampling distribution models, which we talked about briefly, sort of, yesterday when we did the M&M activity, sort of. So we'll go into more detail today. Again, you're supposed to read the first 3 pages of the chapter yesterday, so you should have some sort of frame of reference between the activity and the reading about what I'm talking about today. Okay. All right. So first of all, what we're talking about with sampling distribution models, it's called the central limit theorem. That comes up every once in a while. They call it that. If not, they'll just talk about sampling distribution models. But so if you see central limit theorem or CLT, just know we're talking about sampling distribution models. We're talking about things out of this chapter. Okay, we'll get into more of that later. Anyway, so here's the deal. With the M&M example yesterday and with the ghost example from the book, all right, if I started asking you if we could make a histogram of all the possible samples of a specific size. So yesterday we were kind of doing that. We weren't doing all the possible samples. We were kind of trying to simulate what that would entail, right? Here in the book, we're still talking about the ghosts that we mentioned yesterday. So if you could make a histogram of all the possible samples of size, whatever, and their associated proportion for yesterday's proportion of orange M&Ms, the other proportion of ghosts, you should hopefully be able to visualize that, all right? You should be able to figure out what the center is going to be. So if you think about the activity yesterday, Mars Company claimed that 20% of M&Ms should be orange, right? Unless something drastic has happened, we're going to trust that's true, right? So if they claim that 20% of M&Ms are orange, then what would the center of our histogram be at? Should be at 20%, right? Because that's what they said. So every sample is not going to be the same. You saw that yesterday. We've talked about that before. Every sample is going to be different. But if you put all those samples together, the center is still what they had claimed it to be, right? Okay? And then if you start thinking about the shape, well, you have the center. You saw this a lot yesterday. You had a lot of data centered around point 2. But then, again, there's variability between samples. So it was kind of unimodal and symmetric, right? So we have a unimodal and symmetric distribution with a center at what the proportion is claimed to be. And so then if we could figure out a standard deviation, then we could be able to use the normal model, right? If we could use the normal model, we would be in good shape because we know lots of stuff about the normal model, and that way I wouldn't have to like make up new things or remember more stuff, right? With the normal model, we can find probabilities. We can talk about things that are unusual. We know what it should look like, right? There's lots of things we can do. So that would be very helpful. So our sampling distribution model is what we talked about yesterday, all the proportions from all possible samples. Again, it's completely theoretical. You could not feasibly do that. Okay? You could not take all of the M&Ms, let's say we're doing sample size of 100 M&Ms out of, let's say there was a batch of 10,000, all right? You are not going to feasibly going to go sit in a room with 10,000 M&Ms and take 100 M&Ms and sample them, and another 100 M&Ms and sample them, and keep sampling all of the possible samples of 100 M&Ms. It's just not going to happen, all right? So it's not really feasible, but we use it, this theoretical idea, that's why I call it a model, so that we have something to base conclusions on in chapter 19 and 20. Something to use. Okay? Questions about that? Talked a lot about that yesterday. So, because we have a unimodal and symmetric distribution, then we can have a normal model, and that's going to be nice. Now, a normal model has 2 parameters. Right? A normal model has a mean and a standard deviation. We've already talked about what the center of our distribution was going to be. Yesterday it was at 0.2, right? The ghost example, it was at 0.45. So we expect the center of our distribution model to be at P. And P just stands for the true population proportion. Okay? So P is what they tell you. In chapter, not so much in here, but a little bit, but more so in 19 and 20, there's 2 different percentages you have to keep track of. You have P and you have P hat. which is your sample proportion. So yesterday in your activity, your 20% was what they told you from the Mars company. That's P. They told you that for all their M&Ms, 20% are orange. So that's the true population proportion. In all of your individual samples, though, you didn't get 0.2. So P hat would have been any one of your given samples. So if you're doing a sample size 50 and you got whatever percentage, that would have been P hat. Okay? So make sure you're keeping track of that notation because you're going to have two different percentages to keep track of. And we use them differently in different ways, in different contexts, like formulas and things like that. So you just got to know which one's which. Okay? Okay. So for our normal model, the center is at P, the actual population proportion, whatever the factory or the company or the poll or whoever, whatever they claimed was the proportion. Does that make sense? Then we need some standard deviation to go with that. All right? So that's kind of an issue. However, we know from chapter 17, we had the binomial model. And we could approximate the binomial distribution with a normal distribution, correct? And we could find the mean and standard deviation of the binomial model. We had formulas for that. And the formula for the standard deviation was the square root of n times p times q. Okay? So what we do is we use that to come up with our standard deviation for proportion. All right? We just, since we're looking for, instead of the number of successes, the proportion of successes, because we're looking at proportions or percentages, then we just divide by the sample size. So our standard deviation we're going to use for this model is always going to be the square root of p times q divided by, again, p proportion, q sample size. Is everyone okay with the notation for that and what all those letters stand for? Okay. Now, luckily for you, you don't have to memorize that. We'll talk about that in a second, but you don't have to memorize that. You have to know that for proportions, you have a sampling distribution model that's normal with the mean at p and a standard deviation of something, but I'll show you where you can find that so you don't have to memorize it. Okay? Questions so far? We know why we can use a normal model. We're okay with that. And we know the normal model has to have a mean and standard deviation so we can draw it. Right? Okay. So this is just generic. Normal model, mean of p, standard deviation of square root of pq over n. And so if you were going to draw it, you'd have the mean in the middle, and then plus 1 standard deviation, 2, 3. That's all that means. Everyone go with that. All right. So it goes on. This is just the example for the ghosts. All right. So how good is the normal model? How good is it for our purposes for these sampling distribution models? So let's think about some things. Yesterday with your activity with the M&Ms, the first sample sizes were of 5. Right? We graphed that, right? When we graphed that, it wasn't a histogram so much because if you have 5 M&Ms, you're looking for the percent that are orange, you could have 0 orange, 1 orange, 2 orange, 3 orange, 4 orange, or 5 orange, right? So you could have 0%, 20%, 40%, 60%, 80%, or 100%, and those are the only options. So if we graph those, and I know your class is smaller, right? But if we put all the data together over years, we put all those data together, you would still only have those percentages available to you. So it's less of a histogram as it looks like a bar graph, right? Because there's gaps in between. If there's gaps in between, is a normal model really a good approximation for that? Not so much, because a normal model is fluid, right? So when you have all those gaps, not so good. The same thing kind of happened when you had sizes of 10. You had 0%, 1%, 2%, 3%, 4%, et cetera, et cetera. Okay? So you could only be certain places. So because of that, we have a set of assumptions and conditions that must be met to use this model. I'm going to make a big deal about the assumptions and conditions. Because, like I said at the beginning of the class, you're going to use sampling distribution models for everything we do in Chapter 19 and 20. And in order to use one, you have to check the assumptions and conditions every time. And when I say check them, I don't mean write the title down and put a check mark next to them. I mean actually explain them. So you won't listen to me one time, and you'll think that I'm lying, and on a quiz, you'll just write, the conditions are met, and you'll miss like 4 points, and you'll be really mad at me. And then I'm like, I told you so, and then you'll get over it and start writing them. So practice it on your homework. Don't like skip through it, like actually write it out. Practice them, make sure you know them, okay? Everything we do from here until the end of school will have some set of assumptions and conditions. They're all very similar, but it should be it's going to become this part of the process. And eventually it won't be so bad, and eventually you'll just get over it, okay? But for the moment, you're going to be like, oh, the right stuff. Okay. We have 2 assumptions that are then backed up by 3 conditions. If you're assuming something, you are just assuming it. But the conditions back up that assumption and give you some credibility to that assumption. All right? So we have 2 assumptions. We assume that each sample is independent of the others. Okay? And we assume the sample size is large enough. So we assume our samples are independent, and we assume that the sample size is large enough to proceed. That's what we're assuming. Again, those are going to be backed up by 3 conditions. And when I do the examples today, I'll try to write them out and model that really well, how you should do that on your homework and on your quizzes, etc. All right, the first condition backs up the independence assumption. And that's you are showing that randomization has been employed somehow, some way. If you did an experiment, aren't you supposed to randomly assign people to treatment groups, etc.? Yes. So to tell you that in a problem, and you should say randomization was employed to assign plants to treatments or whatever. Okay? But you want to make sure randomization was employed for an experiment. If you have a survey, we talked about surveys, a well thought out and planned survey should somehow involve some sort of simple random sample or something, right? Whether that be simple random samples are all the basis of all the other sampling methods too, right? So stratified, cluster, all those are based on SRS, systematic. So you would say the survey employed a simple random sample. So you're explaining to your audience, which, let's be honest, the audience I'm referring to is pretty much the AP graders, right? Because it's going to come up on free response question. You're informing them that you know that these things have to be met, and you're explaining to them how it was met, right? So randomization was employed somehow. If there was a weird sampling design, you just want to make sure that the data are representative of the population. Okay? At the very least. So you want to make sure randomization condition is met. The next, the 10% condition that also backs up independence. If you have a population of 10,000 people and you take a survey of 9,000 of them, it's hard to say then that your responses are going to be independent. Because now you surveyed 9,000 people out of 10,000, they're bound to have talked to each other or something probably happened. Okay? So we don't want to survey too many people. We don't have a sample size that's too large. Okay? So to ensure independence, we want to say that your sample size is less than 10% of the population. You should still be able to do a pretty good sized sample. You just want to make sure that you can still ensure that they're unbiased results. All right, so we assume that they're independent. We back that up by saying the randomization was employed and that less than 10% of the population was used. The second assumption was sample size. We need N to be large enough. For proportions, there's an answer to that. For large enough, we go back to what we did with our binomial approximation. We did the normal model back in chapter 17. We want to make sure that NP and NQ are both greater than or equal to 10. You can't write that out and put a check mark. You actually have to put the numbers in and give me a number. Okay? So, the first two conditions, backup, independence, and the last one, success, failure, is what we call it, backs up sample size. If these three conditions are met, then we can assume our assumptions have been met, and so we can move on and use a normal model. If one of them is not met, then we can't use the model, and so then we're going to be out of luck. Now, you know how our book is. So in some of the problems today, they're going to ask you to do all the stuff, and then the last step, they're going to say, are the conditions met? And they won't be, because that's what they do. In real life, this is going to be like one of the first steps of things you do. All right, in chapter 19 and 20, one of the first things we do is going to be check the assumptions and conditions. Because there's no point in doing all the other work we're going to do in chapter 19 and 20 if you can't do it to begin with. Right? If you can't use the model, you can't do everything else. So it's going to be one of the first things you do. So don't go buy the book today when it's like, oh, by the way, did you check those conditions? All right. Everyone go okay with these conditions? It's not like you're writing paragraphs and paragraphs and paragraphs. You're just making sure that you'll have like 3 little sentences, 3 little phrases. Make sure you're done. Okay? Everyone go with that. All right. Then, here is the sampling distribution model portion in summary. We've already talked about all of this. We're going to use a normal model, assuming that the samples are independent and the sample size is large enough. So assuming all the conditions are met, we're going to use a normal model with a mean of p and a standard deviation of the square root of pq over n, which happens to be, conveniently, on the AP formula sheet. So on the AP formula sheet, the one I have in class, I have 2 pages superimposed on the front, right? Like they're not superimposed, but 2 pages on the front. And then I have 1 page on the back, which we haven't used yet. So you haven't even looked at the back of it. We're going to start looking at the back. So this is the back of the formula sheet. So I have these 2 pages smushed together on the front, and then this page is on the back. All right. Now it tells you, if you're doing a single sample, it gives you 2 statistics you could be using, a mean or proportion. Well, right now today we are talking about proportions, right? That means everything we're doing has to come down to some percentage. Tomorrow we're going to talk about means, because obviously not every single survey yields a percentage, right? Sometimes you're looking for an average shoe size. That doesn't come down to a percentage, that's an average, all right? So we're just dealing with proportions today, we'll deal with means tomorrow. But we've got proportions, and it tells you the standard deviation for sample proportions. The square root of p times the quantity 1 minus p, which is the same thing as q in our book, divided by n. All right, so you don't have to memorize it, you just need to know where to find it. We're good with that. Okay. That's pre-calculus. You don't want that. Okay. When you have a normal model, then we can start answering questions. We can draw the model, we can find probabilities, we can tell if a certain percentage is unusual, right? And all those things we're going to do in chapter 19 and 20 that's going to help us out. So let's do some actual examples. Now, I will do it all the way through if you want me to, but otherwise I think most of the stuff we've done enough that I'm not going to have to sit here and draw it all out and waste your time. If you want me to do something, let me know. Okay? So it says, in a large class of introductory statistics students, the professor has each person toss a coin 16 times and calculate the proportion of his or her tosses that were heads. So I could have done that yesterday instead of M&Ms, right? We could have flipped a coin. The students then report their results, and the professor plots a histogram of these several proportions. So in part A, what shape would you expect this histogram to be and why? And in part B, where do you expect the histogram to be centered? Let's start with B. Flipping a coin, trying to find the proportion of their heads out of 16. What do you expect the center to be? In percentages. 0.5. You would expect 8 to be heads, or 50% of them, right? Talk about proportion. So we would expect the mean to be the true population proportion, which is 0.5. Everyone go with that. If we start thinking about what the histogram would look like, the center would be at 0.5. What would the shape be, do you think? What do you think the shape would be? Probably unimodal and symmetric, right? You have, a lot of the time you're going to get around 0.5. Some people might get more that are heads, some get less, right? So we're thinking generally unimodal and symmetric. Would you agree?
Yeah.
Okay. On part C then, how much variability would you expect among these proportions? All it's really asking you is for the standard deviation. You have a measure of center, and you talk about shape, and we have to talk about spread too, right? Our measure of spread then would be the standard deviation. Since we're assuming it's unimodal and symmetric, and we know the center, we can treat this as a normal model, hopefully. And so we would find the standard deviation by doing the square root of p, which is 0.5, times q, which is 0.5, divided by the sample size. They tossed a coin 16 times, so 16. And that comes out to be 0.125. So that would be our standard deviation. Everyone good so far? On D, explain why a normal model should not be used. Like I said, our book does things backwards. So I'm going to go through this one time and do all the conditions and assumptions. Exactly how you should do on your homework. Okay. Then I won't go through all this. We'll just talk about the rest of them today. First thing, we have the independence assumption. We're assuming that the samples are independent. They should be independent because they're coin tosses, right? We're going to write out our conditions. Is randomization employed? It's a coin flip, which is a truly random event, right? So we just explained that. A coin flip is a truly random event. Let's put this in the context of yesterday with your activity. Was randomization employed when you selected M&Ms? Right, you're supposed to take random samples. You're supposed to shake up the cup and then draw out without looking, right? So you would say randomization was employed in the selection of the M&Ms. Okay. 10%, this one's tricky because it's not really a population. We don't really have a population size here because it's coin flips. Okay, so all we need to say is this is a representative sample. If, again, you put this in the context of your M&Ms yesterday, when you drew 100 M&Ms, is 100 less than 10% of all M&Ms? Yes, that's what you would write. You would write your sample size is less than 10% of all M&Ms, because that should be true. Okay? All right. Then we have sample size. And we're checking success failure. So we have NP, is that greater than or equal to 10, and is NQ greater than or equal to 10? Well, P is 0.5, so Q is 0.5. What's half of 16? So not so much, not greater than or equal to 10. So this condition is not met. If one condition is not met, then you got to scrap the whole thing. Okay? So that is why a normal model should not be used, because the success failure condition is not met. Questions about that? All right. On number 7, suppose the class at exercise 5 repeats the coin tossing experiment. The students toss the coins 25 times each. So now we've increased the sample size. What's a half of 25? 12.5. And so half of 25 is 12.5, so that is greater than or equal to 10, so that would be a large enough sample size. All the other conditions should have remained the same. All right, so it says use the 68, 95, 99.7 rule to describe the sampling distribution model. So on part A, I'm not going to do this unless you want me to. All it's asking you to do is to draw out the model. We know the mean is at 0.5. The standard deviation is not what it was in number 5. Why is the standard deviation different from here? Right, we changed the sample size. Right, we have to divide by n. Well, we don't have 16 anymore, we have 25. So we would need to recalculate the standard deviation, but then we could add and subtract that from the mean to get our 1, 2, and 3 standard deviations outside the mean. You would draw in the 68, 95, and 99.7 percentages, and you would label it. So you would write percent of coin tosses resulting in heads, sample size, or n equals 25, because that model is going to change if your sample size is different. Okay? So you want to make sure you label it. That's all it's asking you to do in part A. Do I need to draw that out? Okay. In part B, confirm that you can use the model here. I'm not going to write this all over again. You wouldn't have to either, because you could just see C number 5, part D. All right? Your independence assumption, randomization 10%, those should stay exact same. Haven't changed anything. Still the same scenario. The sample size condition was not met in part D number 5, so we would show that it is met now. Right? We talked about that a second ago. 12.5 is greater than or equal to 10, so we should be good to go. They increase the number of tosses to 64 each. Draw and label the appropriate sampling distribution model. Check the appropriate conditions to justify your model. The conditions are the exact same except for success failure, because now sample size is 64. Right? Your model is going to be different because you change the sample size. You have to change the standard deviation. Right? Because now you're dividing by 64, not dividing by 25. But you could still just draw out the model and label it. It wouldn't be a big deal. Are we good with that? Then in part D, explain how the sampling distribution model changes as the number of tosses increases. So let's talk about shape, center, and spread. As the number of tosses increases, does your shape change? If at all, it becomes what? More unimodal and symmetric. Depending on number of tosses you started with, right? So if anything, it gets more unimodal and symmetric. Does your center ever change? No, because they should all be centered at what? 0.5. Regardless of the number of coin tosses, it should always center at 0.5. Does the standard deviation change?
Yes.
Obviously, because we've already changed it 3 times in the past 5 minutes, right? So if the standard deviation changes, then what's happening? So this is what we're going to talk about. As your sample size is increasing, your model is becoming more unimodal and symmetric. So what is happening to the variability? Are you becoming more variable or less variable? Less variable. So as your sample size increases, your standard deviation is decreasing, your variability is decreasing. Right? It's becoming more compact around the center. That should make a lot of sense. If you have a population of 100 of something, right? The more people you survey in your sample, the closer you should get to the true population proportion of whatever you're asking. Because you're getting closer and closer to the real population size. Okay, so as your sample size increases, your variability decreases. Everyone okay with that? Okay. And number 9, one of the students in the introductory stats class, exercise 7, claims to have tossed her coin 200 times and found only 42% heads. What do you think of this claim, and explain? All this question is really asking you is if you think 42% is unusual. If you're trying to decide if that's unusual, what should you do? You'll need to not necessarily draw the whole model, but make something so you can look at the standard deviations, right? 42% is below the mean, because what's the mean? 50. We would need to figure out the standard deviation because, again, the sample size is now changed to 200. So the other ones we had were 16, 25, and 64. So we need to recalculate the standard deviation. And we would take 0.5 and we'd start subtracting that standard deviation so we could get that 1, 2, and 3 standard deviations below the mean and decide where 42% fell, right? Generally, we say if it's lower than 2 standard deviations below the mean or 3 standard deviations below the mean, then it's unusual, right? Personal opinion, there's no right answer there, 2 or 3, so pick one and stick with it, right? But that should be your justification. Does that make sense for number 9? Okay. Another question, I'm not going to do the whole thing, I'm just going to make sure we understand some things. Based on past experience, a bank believes that 7% of the people who receive loans will not make payments on time, and the bank has recently approved 200 loans. So they're giving you P, and they're giving you N, right? A says what are the mean and standard deviation. Blah, blah, blah. You could do that, not a big deal. B, what assumptions underlie your model and are the conditions met? You could do that. I want to talk about C. What's the probability that over 10% of these clients will not make timely payment? How are you going to find a probability?
You got a first time maybe the standard deviation.
Yeah, you're getting standard deviation. That's a good start.
Yeah.
It's that thing in your calculator. That's good. Normal CDF. With normal CDF, you can calculate a probability using your boundaries and your mean and standard deviation, right? It says over 10% of these clients will not make timely payment. So you're going to do 10% to infinity, quote unquote, right? Infinity. And now we have the ability in your calculator, because I told you, you can substitute the mean and standard deviation into the calculator, and it'll tell you the probability. Questions about that? Questions? Now, here's a very important thing for you to know about your like AP exam type thing. If you write out everything in the calculator, like normal CDF, and this is what you write as your work, that will not suffice. That won't do. You will get 0 credit. They don't like that.
What do?
You might get credit if you write this out, and then you label this is the lower boundary, and this is the upper boundary, and this is the mean, and this is the standard deviation. So that might get you credit sometimes. That doesn't guarantee you get credit. That's just depending on the year and who decides they're grading it. So that might get you credit. The better plan is to do this in your calculator and get the right answer, but to make a quick sketch, put in the mean and the standard deviations, and then just draw in where 10% would be and shade the direction you want. If you do this, and then calculate the probability in your calculator, you'll get full credit. Because you've shown that you're using a normal model, that you know what section of the model you're looking for, you know that you're looking for an area under the curve, which is the probability, and that you know how to calculate that. If you write the calculator function down, then it's showing that you memorized the calculator function. So I'm just giving you the heads up there. Okay? Any questions on any of this stuff, though? So everything's based on normal models. We're good? Mm-hmm. All right, I'm going to give the assignment then. And then tomorrow we won't do as much. Tomorrow we're going to do all of the same stuff. I did a really good job, I feel like, today of setting this up. So tomorrow we're going to do the same thing, but for means. So I want to do all the background stuff. We'll talk about what happens when we have means instead of proportions. Okay?